Okay, we're going to do part 1 of section 1.6. And these are tangent graphs. We will get to secant and cosecant graphs. We're going to start with tangent curves, tangent graphs. And what I'm going to do is show you a website that actually has some graphs on it that we want to review first. So I'm going to let you see the sine curve. It's a pretty good website. It's called Math Open Reference, and it gives you lots of resource material. And it's got a little animation thing of the actual sine curve and the cosine curve and the tangent curve. So it takes a few seconds to load because it's got the little thing in that we can use. And it shows you, on this one, it's specializing on the sine graph, the sine curve. And you can see that this, if we started at 0, so you see I'm at 0 degrees right here, that my red dot is at 0. Because on your chart, if you had your chart, the sine of 0 was 0. And we always start our sine curve. We know it's a bow tie graph, so you can see the shape of the bow tie right here. And it always starts at 0, has a 0 in the middle, and has a 0 at the end. That's our sine curve. Now, as we drag this around the circle, you can see what happens to your red dot. Because the red dot's moving, and right now this is not behaving very well. Okay, so it goes to a maximum, comes back down at 180, it comes back down to a 0. Then as we go down to 270, it's back down to a minimum, and then it comes back up to 0. Now I could keep going, and watch what happens to the curve. It just keeps moving. And you could show radians if you wanted to. You could show degrees. And sine and cosine are both continuous curves. They don't have any breaks in them. As you go around the circle, as you make different rotations, it's a continuous curve. Now, if you look at the cosine graph, again, it'll take a second or two to load. You'll see the same kind of thing where it's a continuous curve. It almost looks like the exact same graph, except where does the cosine start? At the maximum. It starts at the top instead of starting at 0. And it does the exact same curve. So you'll see that as this comes up. Okay, so here's the cosine. And if I'm at 0, you can see at 0 degrees, it starts at a maximum right up here. You see the red dot is right up here at a maximum. And as you go around the circle, you go to your intercept at 90 degrees, you go to your minimum, watch the red dot, it's moving, it's back up to the intercept and back at the top, and as you keep going around, it's the exact same curve, except on the axes, they're always going to be maximum value. And there's 2 intercepts on your V's there. So that would be the cosine graph. Now I'm going to let you see the tangent graph before we graph it. Now if you could, take out your chart that I gave you, the chart, if you have it. I mean, it's not mandatory, but if you have it, it will make a little more sense. So if you have your chart, they look like this. Now I want you to take a look at something for a second. And if you don't have one, just look up here. Look down the sine and the cosine columns. If you look down those 2 columns, there are no undefined areas. It is a continuous curve. Did you see when I went around the circle? The curve just kept going. There are no breaks in the sine or the cosine graphs. Now look down the tangent column. There are 2 places where it's undefined. Those are called breaks, that there's no value for that. You cannot graph something that has no value. So we're going to use something special. Now let me show you what a tangent graph would look like. Here's the tangent function. It takes a second to load. As you look at it, let me just go review something on the tangent column here. Tangent at the very top, the tangent of 0 is 0. So the tangent and the sine are both going to start at 0. As you go down the tangent column, it gets bigger and bigger and bigger, because radical 3 is 1.7. Then it gets to undefined, where there's no value. Then it skips all the way down to negative radical 3. Let me show you what that does up here on this chart, or on this little graph here. Now notice what it looks like. You got a bunch of the same kind of curves. Like I said, if you look at 0 on the tangent, it's going to be at 0. It's going to be right here at the origin. Okay, and if I went to radians here, you could see that it would be 0 radians, and then you got pi over 2, pi, 3 pi over 2, 2 pi, and so on. This is one time around the circle. This is from 0 to pi over 2, or to 2 pi. Now, if I go up the chart, as I go up, you can see the red dots moving. Now, when I get to, let me go to degrees again. When I get to 45 degrees, what is the tangent at 45 degrees on your chart, if you have a chart?
1.
It's 1. Does this red dot look like it's at a 1? Yeah, because this is 0 and this is 4, so 1 would be right around this area. So at 45 degrees, it is up 1. That is the tangent value at 45 degrees. You can see that these are both 7.4s here, because it's a 45, 45, 90 triangle. Now look what happens as you go to the top. Now I'm going to stop just before the 90 degrees. That's like 86 degrees. Look where the red dot is. It's even off the graph because it's getting higher. But has it passed the 90 degrees yet? No, it's because it's 86 degrees. Now what happens when it's actually at 90? Where's the red dot now? It's gone because there is no value for 90 degrees. What happens when we go past 90 is, now where's my red dot? You see it way down here at the bottom? It starts over and makes another one as it goes up the chart. So as we go around, you're going to see it's going to go up again, and then it's going to jump over it again and come back up and do another one and jump over it, and it keeps coming up. That's the tangent curve. It has to jump over these lines right here. Now these lines have a special name, and I'll put it on the notes for you. So let's get back to our notes. Let's do example 1. Example 1 is going to say to graph y equals tangent of x. Okay, so what is it just if I went down the tangent column, what would the graph look like? And here's what it would look like. We're going to draw our x and y axis. And if you look on your chart, or if you look on my chart that I have right here, the tangent of 0 is 0. So I can put a dot right here. The next thing I need to do on my graph is find out where it's undefined. So where is my graph of the tangent going to be undefined?
45.
At 45 degrees, which is pi over 2 radians. So at pi over 2 radians, right here, it's undefined, and that is going to be a vertical line, a vertical dotted line. And I'm going to tell you what that's called in a second. That is a vertical asymptote. Yes. No, you do not. That's a good question. For cosine and sine, you must find the amplitude and the period. For tangent, it goes up and limited until it hits that dotted line, and then it starts back at the bottom again. So no, there's no asymptote, or there's no amplitude. The period you don't need to find because you're just looking for dotted lines. So this dotted line right here represents an area where you cannot graph it. It's undefined. There's no value. It's like you could graph it here, and as soon as it gets to this wall, you have to jump over it. It's like a small wall that you can't go through, but you can jump over. So this is like a wall that it can't go through. It's called a vertical asymptote. Now where's the next one on my graph, on my chart? 270, which is 3 pi over 2, right? So here's 1 pi over 2. This would be like pi. And then this would be 3 pi over 2. That's going to be another vertical asymptote. What about the left side of the graph, way over here on this side? Is there another dotted line that might be over there? How far apart are these? They're a pi distance. So if I went a pi distance this way, where would I end up over here? Negative pi over 2. Okay, so that would be my other vertical asymptote. This has a distance of pi. That's it. This would be a half a pi, and this would be a half a pi, so you got 1 pi distance. 1 pi apart from the dotted lines in a regular tangent curve. I'm going to tell you right now, they use this area a lot more than they'll use this area. Because this area right here has the origin in it. This area doesn't have the origin. This area has the origin, so they're going to use this a lot more often. Now look at if you have the chart, if I went over to pi over 4 radians, which is 45 degrees, what's my tangent? Tangent of 45 degrees is 1. So I go over 45 and I go up 1, and that would be a dot. If I went to negative 45 degrees, or negative 1, that means I'd come up the bottom of the chart, that would be at a negative 1. So this is over negative 1, or negative 45 degrees and down negative 1. You're not going to connect those just like a straight line. The tangent, you saw it on the website, is like a curved graph. It goes like this, and it goes like this, and it gets infinitely close to that dotted line. We'll never touch it. You cannot touch that dotted line because that's an undefined area. Now it can jump over it, which as soon as you go past pi over 2 or you go past 90 degrees, then it starts back here at the bottom and goes up again. So again, you'd have an intercept here, you'd have a negative 1 down here, you'd have a positive 1 over here, and you'd have another tangent curve. As long as you go around the circle, it will keep hopping over these vertical lines, and it'll keep making new arcs, or new graphs like this, new curves. That would be the tangent graph. Those are the tangent values on your chart. Now we could look at some other tangents really quick. There's just 2 more that I want to show you, and then we're done. That'll be done with part 1. That'll be the tangent graph. So what I want to show you, one last thing, is we want to make sure that we find out that x is pi over 2 and negative pi over 2. Because that's where your vertical lines, your vertical dotted lines go. If the tangent's pi over 2, it's going to be a dotted line. If the tangent is negative pi over 2, it's going to be a dotted line. So those are what we're looking for when we graph the tangent. We've got to plug in our dotted lines first, because you can't graph it anywhere else. You can't graph it on that dotted line. So we need to know where those are. They're right here and they're right there. So let's switch it up a little bit. Let's do example 2. It'll say graph y equals tangent of x over 2 this time. I need to find out what I could put in for x to make it equal pi over 2, because that's what would be my dotted line. If I put a pi over 2 for x right now, it's not going to equal pi over 2. It would be pi over 2 divided by 2, which is pi over 4. That's not undefined. I want to find out what could I put in for this x right there that would make it equal pi over 2. What do you think? It's an easy one. Take that x, put in pi, and you got pi over 2, right? So if you were to solve this right here, you would multiply both sides by 2. The 2's will all cancel. You get x equals pi. So pi is a dotted line on my graph. So let me draw my graph over here. I'm going to go over to pi, and I'm going to make a dotted line. Okay, that's what you're going to do first, is you're going to take whatever is next to the tangent and set it equal to pi over 2, because that's where the undefined would be. So take this and set it equal to pi over 2. That will tell you where your dotted line is. Yeah. Every single time for tangent, yeah. You're always going to set it equal to pi over 2 because you want to know where the dotted line would go. Now you're also going to set it equal to negative pi over 2. So x over 2 would equal negative pi over 2. So what is my x going to be in this case? Negative pi. Now what were you going to say? This one is not pi units apart. No, because you're dividing it by 2. You're dividing your tangent, your x, by 2, which is going to increase your period. So your period is now going to be a 2 pi period here, in that case. So you're going to have a dot at pi and a dot at negative, or dotted lines at negative pi. And let me fill you in on a little secret. Whatever you get on one side, you're going to get on the other because it's a symmetrical graph. So once you solve the first one, you basically already have the second one. So now you're going to draw your origin, your 0, and then halfway between it, you'll be at 1. Halfway between those, you'll be at -1. And then you draw in your curve. Now what if I wanted to do another rotation around the circle? Where would my next dotted line go? If I went way over here, this is 2 pi apart from each other. So if I added 2 pi to pi, what would I end up at? 3 pi. So yeah, you'd go over here to 3 pi. You'd have another dotted line. You'd have another intercept, another 1, another -1, and another curve here. That would be 2 rotations around the circle if you needed 2. They're both going to be 2 pi units apart from each other. So that is the graph of tangent of x over 2. Meaning that if you plugged in a pi, it would become pi over 2, which is a dotted line. So your dotted lines had to be at pi and at -pi. Yeah. This one up here? This one, I look at my chart and I look at 45 degrees. At 45 degrees, the tangent's a 1. So I'm going to go over 45 degrees and up 1, basically half. I'm splitting the difference there. All right, let's go to the last example for today. We're going to graph y equals okay, so it's -3 tangent 2x. No amplitude or period. We're using a tangent curve. So we just want to take this 2x and set it equal to what? Pi over 2, because that's what would be undefined. So what would I put in for x to make it equal pi over 2 so I can put my dotted line in? So let's multiply by 2. So those are going to cancel out, right? You get 4x equals pi. Divide by 4. And what is x going to equal? Pi over 4. That's a dotted line right there. What's going to be my other dotted line? Remember, it's a symmetrical graph. -pi over 4. Those are my symmetrical graphs. So I'm going to draw my x and y axis. I'll put a pi over 4 line. I'll put a -pi over 4 line. Make a dotted line at pi over 4. Make a dotted line at -pi over 4. Where do I know that the tangent has to touch? At 0, right? Tangent of 0 is 0. That's always going to be on your tangent graph. 0, 0 is always going to be a point. Now, what is this -3 going to do to my graph is the next question. Well, let's just see what happens if I put in well, what would have been, let's say the tangent came out as a 1. Let's say that this came out as a 1. What's 1 times -3? -3. So if I would have normally would have gotten a +1, what's going to come out now? -3. So actually, instead of going over to 45 and up 1, we're going to go over to 45 and down 3. Because it's a -3. It flipped my graph around just like it did in sine and cosine. This normally would have been down 1. This time it's going to be up 3. So it's going to be up here. So my curve is going to look like this. You see how the curve got flipped around? It used to go up on the right side and down on the left side. Now it goes up on the left side and down on the right side. So the cosine curve, or the tangent got flipped there. Yeah, it got flipped because this 3 was a -3. If it was just a +3, then it would have still gone the same direction. It just would have gone up to 3 and down to 3. So the negative is what flipped it over. All right, so that was part 1 of your notes.